academics, he is actively contributing to professional societies like IEEE, INAE, ISTE, and IE, and engage in outreach through expert lectures, workshops, and conferences worldwide. His work in cyber physical system, load frequency control, renewable energy, and power system stability has had a lasting impact in the field, and he continued to be a leader in academia and research. So, welcome you, sir. So we will start the session now.
Okay.
You can start now.
Okay, may I audible?
Yes, sir.
Okay. Thank you, Dr. Rupali, for nice introduction. So, first we actually share the screen. This is visible, everybody?
Sir, the mail is visible. No
Okay.
slide.
Sir, the slide is visible. Now it is visible, sir.
Okay. Thank you. This is visible now? Hello?
Yes, sir, it is visible.
Okay. So, good afternoon, everybody.
Good afternoon, sir.
So, today I just present the very brief topics, actually the mathematical modeling of the wind energy system. First, we actually discuss about the what is the requirement of the renewable energies, what is actually significance of the wind energy system, what is the basic structure of the wind energy, and then we actually consider maximum power point taking control, and if the time is permit, then we actually consider the small signal stability analysis. Now, what is the requirement of the wind energy system or renewable energies? Because every day the energy is the major input to overall socio-economic development of any society. So per unit consumption of the power is day to day increasing. From last year to this year, the 11% the per unit capacity is increasing in India. So only the conventional energy source is not sufficient to supply the whole power. So that point of the view, the alternative arrangement is actually the renewable energy or the carbon-free approach. So this is actually the so renewable energy is the alternative approach to supply the extra energy to the system. So day to day, we actually the most prominent energy we actually consider from the solar point of the view, but the wind energy is the another emergent techniques actually to supply the power to the grid. So this is the first state going renewable energy, and this is actually we can find out the what is the maximum energy we actually put the system. So that point of the view we require. So concept of the wind energy, how the wind energy, what is the mathematical model of the wind energy system, what is the different type of the cause, advantages, disadvantages of the wind energy systems. So the when we actually find out the wind energy, so first thing actually you should know what are the wind power potential. Wind power potential is actually depend on the wind power density of the system. The wind power density means actually the coastal area where the wind density is very high. So that energy we actually take from the system. So mainly the wind energy, when we actually consider the wind power system, we mainly consider the coastal side of the our India. So this 10th state actually mainly significant amount power supply to the on the wind energy system. Tamil Nadu, Gujarat, Maharashtra, Karnataka, Rajasthan, Andhra Pradesh, Madhya Pradesh, Telangana, and the Kerala and other state is actually. If we go through if we see this system up to the 31st 2025, the on the total capacity is you can see that the 50,037. So if we consider the system, so 500 gigawatt power we actually supply to the our system. So mainly the contributed state is the Gujarat, Tamil Nadu, and the Andhra Pradesh means that the coastal area. You can see that the only the coastal area, this part actually mainly supply the wind energy on the system. So now the how the fundamental equation wind power means the what parameter is actually depend on the wind energy in the system. So wind power depends on the amount of the air, that is the volume of the air, speed of the air, mass of the air, and the falling through the area of the interest, that is flux. So if you see that the total kinetic energy definition, so we know that this is the half equal to mv square. V is the total velocity of the system. So velocity is actually the power in the per kinetic energy unit time, that is the half m dot v square. M dot is equal to dm by d, that is the total mass flux. So the fluid mechanics gives the mass flow rate dm by d rho av. So total power, that is the main important half rho. Sorry, this is the half rho a v cube. So the power is directly proportional to the v cube of the system. V is actually the what is the velocity of the wind. So the total power output, or you can under total energy produced from the wind is depend on the v cube, mean the wind speed, v cube of the wind speed, that is the cube of the velocity of the wind. So the total power is actually depend on the cube of
Sir,
the velocity,
sir,
air
sorry to
density,
interrupt. Your slides are not changing.
the rotor shift area. So the shift area means actually the what is the wind actually, which area the wind actually flow from
Excuse me,
the
sir.
your.
Sir,
Hello.
sir, the slide is not changing.
Okay, okay. Now this is changing.
Yes, sir. Yes, sir. Sir, can you change next slide so that we can sure?
This is now.
This is now installed wind capacity by state.
No, fundamental. Okay.
A fundamental equation is now.
Now this is changing.
Yes, sir.
Hmm?
Sir, Sir, now it is in fundamental equation of wind power.
Then efficiency of this thing is there.
No, it is not coming next. Now it is coming. Wind energy production system.
Okay. When this is okay, one by one. ठीक. Now we actually go through the fundamental equation of the wind power. This is actually visible, na? Fundamental equation of wind power.
Yes.
Yes, sir, it is visible. Yes.
We actually, when we actually see that the fundamental equation of wind power, we see that there is the three parameter is actually there. So first is actually the amount of the air, speed of the air, mass of the air, and the flowing through the air of the interest, means the which area the wind is actually flow from the system from one part to the another part. So total kinetic energy in the system is actually depend on the half m square. This is the well-known equation, and mass rate is actually the dm by dt. So at the fluid mechanics gives the mass flow rate is equal to rho AV. Rho is actually given the total air density. A is actually represented by the which area the wind is actually flow from the one side to the another side, and V is the actually velocity. The total, if you put the your total kinetic energy means the total power. So this is the half m dot v square. So if you put this part m dot in the equation, so total power is actually depend on the these three quantity. One is the rho A and the VQ. So the rho is actually the total air density of the system. A is the total area, and the V is actually the cube of the velocity of the wind. So total power mainly depend on the velocity of the wind. So if the wind velocity is the high, so we got the maximum power from the system. Now, what is actually the efficiency? When you actually find out the what is the output power, so this is the extra power from the wind. So that is actually you can consider the P equal to half rho A VQ, but the output of the power is actually totally depend on the power coefficient. So the power coefficient CP is actually depend on the PT divided by PW. PT is actually represent the turbine power. That is the efficiency of the system. Actually, you understood this. PW is actually total power extract from the wind, and PT is the actually the useful power of the system. So if we represent the turbine power output, that is not the PW. What is actually power produced? That is actually the PW into CP. That is actually given the PT. That is the turbine power output of the system. The CP value is the 16 by 27. That is actually the Bush limit, the maximum power. Only 59% power we actually utilize. On the when we actually go to the wind turbine system, only 59% power we extract from the system. So the wind maximum efficiency of the your system is actually the 59%. So 59% power we actually extract from the wind system. Now this is the actually total wind power production. If you actually represent the wind system, how actually you can put the wind power to the gate. So this is the fourth part is there. One is the what we actually discuss, that is only the aerodynamic part. Another is actually the mechanical part and the electrical part. So there is a three different parts of the wind power energy production system. If we divide the total wind power energy production system, so this is the three part is there. So one is actually the aerodynamics part. That is the how the wind power is actually extract from the your system. Second part is actually the how this wind power is convert to the mechanical power. That is how actually rotate the generator. And the third part is the how this power we actually incorporate with the maintain the your voltage and frequency. How actually you can put the to the gate. So this is the three part we actually consider from the wind energy conversion system. So first you can see that the power conversion or power control, power transmission, generator, that is the power conversion from the your mechanical power to the electrical power. Power converters is required to the maintain the your voltage and frequency, and that is actually put to the gate. So the wind turbine, if we consider the these three part, if we what is the main contribute part? So first part when we actually consider aerodynamic part, when we gearbox, because the wind speed is very low, so within the gearbox, that is the convert the low speed wind turbine to the high speed of the generator. The mechanical speed regulation is actually required to blade pitch angle control. That we discuss what is the pitch angle control. Different the controller is actually there. So the one controller is actually the mechanical side. That is the blade pitch angle controller is there. When you actually go through the stall controller, no pitch actuator is required. That is the fixed speed when turbine we use. Type of the different of the type of generator depending of the your systems. That is also discussed. What is the different of the generator we actually use, the induction generator, synchronous and W-phase induction generator. And nowadays actually the wind turbine has a 25 kilowatt to the 3 megawatt. Now we have the 5 mega up to the 5 megawatt generator, wind turbine generator is also there. So this is the type of the wind turbines. If we consider, this is the depending of the position of the wind turbine, we actually divide the three parts. One is the onshore wind turbine, near shore, and the offshore. Onshore wind turbine is placed in the hilly and the mountain place, and at least 3 kilometers away from the nearest shore. So this is the away from the onshore wind turbine is actually, this is not the shore. This is the minimum 3 kilometers from the shore. Near shore wind turbine are installed within the 3 kilometers from the nearest shore or the water within the 10 kilometers from the land. And offshore wind turbine developed in the zone at least 10 kilometers away from the land. So nowadays, actually, mainly we emphasize in the offshore wind turbine. Previously, we actually put the wind turbine is actually the onshore. Nowadays, what is actually the research is actually going on. Maximum energy is actually coming from the offshore wind turbine. So but different challenges are also there in the offshore wind turbine. But the research is actually going on how actually maximum energy we extract from the offshore wind turbine. Now, depending of the your construction point of the view, the wind turbine is also depend on the two type of the one is actually the horizontal axis wind turbine, another is the vertical axis wind turbine. This is actually the just construction point of the view. We not go to the details about this system, but only for the understanding point of the view. So what is the different of the wind turbine actually there? So there is a two type of the wind turbine we actually use the horizontal axis wind turbine and the vertical axis wind turbine. So horizontal axis wind turbine is actually mainly the high maximum efficiency we consider. This is the high conversion efficiency and power regulation and the pitch angle control is the high wind speed. Actually, when your high energy conversion is required, so there we actually use the horizontal axis wind turbine. And there is the main disadvantage of this type of the wind turbine is there. So longer cable is required for the high tower and installation cost is very high. So when we actually use the wind farm, so there we actually use the horizontal axis wind turbine. But when we actually individual wind turbine we use, so there we actually use the vertical axis wind turbine. Because the horizontal axis wind turbine initial cost is very high. Efficiency, the advantages is there. So efficiency of the wind turbine is very high because this is actually the high meter wind turbine. This is the 15 meter. This type of the wind turbine we actually use for the horizontal axis wind turbine. So mainly the advantage of the horizontal axis wind turbine is the high conversion efficiency, power regulation, and the pitch angle control is the high. What is the pitch angle? We actually discuss about this thing. Vertical axis wind turbine construction is the operational independent of the wind direction. So this is actually the individual if we use the any wind turbine. So there we use the vertical axis wind turbine concept. So lower installation and easy maintenance cost due to the ground level gearbox of the generator and having the low but the disadvantage is actually the low conversion efficiency. And the main advantage is actually in the horizontal axis wind turbine, your direction, the wind is required and which direction the wind actually flows through your system. But the vertical axis wind turbine, you can see that all the side, this is actually system is rotated. So that point of the view, the wind direction is not required. This is the main advantage, but disadvantage is that the efficiency is very low. So what is the major components of the wind energy conversion system when you actually use the system? This is the total detailed diagram of the system. First, you can see that this is the required wind turbine gearbox. This is the mainly the gearbox is actually the when we use the wind turbine, due to the wind speed, the speed of the wind turbine is very less. So, to the gearbox, this is low speed high speed system, and that is actually connected to the different type of the wind generator. Depending of the type of the generator, the 5 different type of the wind generator is there. So depending on the wind, we actually use the any type of the generator. Either this is a squirrel gauge induction generator, wind rotor induction generator, W-fed induction generator, permanent magnet synchronous generator. Depending on your conversion efficiency, we actually choose the generator, which type of the generator we use for the your system. And after that, we use the generator as a harmonic filter, because the filter circuit is required to the put the converter. Before the converter circuit, we use the generator side filtering, and there is a two filtering. One is the gate side. You can see that your wind energy converter this side, and after power converter gate side harmonic filter, two filter is required. Then the step up transformer, and then so three part is, again I repeat, this is the three part. So wind turbine, this part, when you actually consider wind turbine part, so this is actually the aerodynamic parts, then your electrical parts, and then we actually go through this is the mechanical part, then the electrical part is there. So three different part is the aerodynamic parts, mechanical part, and the electrical part is there. Now, what is the different configuration of the wind turbine? How actually choose the which type of the generator we use, and what is actually the criteria? So depending on that, the 5 different type of the wind generator, wind energy conversion system is there. Depending on the generator, we use the 5 different type of the wind generator. Type 1, that is the fixed speed wind turbine, wind energy conversion system. That is, we use the squirrel gauge induction generator. This is the initially wind turbine when we use. So there we use the squirrel gauge induction generator. The advantage is they are very small. Installation cost is required, but disadvantage is there. This is the fixed speed wind turbine. If the wind speed is increase or decrease, this is not change every time. Depending on that, every time this is actually use the fixed speed wind turbine. So this is a fixed speed squirrel gauge induction generator without any power converter is actually required here. Only the bypass switch is sufficient to control your systems. The main drawback of this system, the low wind energy conversion efficiency, and change in the wind speed are reflected to the gate. Mean that this is actually the fixed speed wind turbine. So if there any type of the fault is occur in the system, there is no fault right through capability is there. So any type of the fault or any disturbances occur in the gate, suddenly this total wind turbine actually disconnect from the gate. Initially we use this type of the wind turbine. Nowadays we actually discard this type of the wind turbine, but this is the basic first step when the wind energy is there. So actually Dennis actually first install the coming from the wind turbine system. So there we actually use this type of the wind turbine. This is the type 1 wind turbine system. Type 2 wind turbine is the semi-variable speed. 10% wind conversion is actually 10% means the plus minus. This is actually just like if the 1500 RPM system. So you actually 10% below and 10% above variation is possible to the wind system. So the semi-variable speed wind energy conversion system is there. So this is also the main disadvantage. Only the variable register wind turbine we actually this is the wound rotor induction generator. So depending on your resistance, we actually change the wind speed. But this is also the disadvantage is there. So limited speed range and low energy conversion efficiency. The mainly nowadays, what is actually we use that is the W-fed induction generator. The 85% wind generator is actually nowadays actually W-fed induction generator. So the main advantage is there. So this is the wide range, 30% plus minus speed is possible on the system. Here the back-to-back converter. Why it is called the W-fed? Because the two way the system is actually feed. One is directly connected to the stator. Another is actually the rotor is connected to the gate through the back-to-back converter. So the efficiency is very high, and we actually mainly the 85% wind energy nowadays actually we use the doubly fed induction generator. The new generator, what is actually the new concept is actually coming into the picture, that the PMSG, permanent magnetic synchronous generator, wound rotor. This is the 100%. Previously, up to type 3, you can see that only the 30% energy conversion is possible. But when we use the full speed 100%, this is the 100% wind energy conversion is possible to the permanent magnet synchronous generator. So this is the full capacity. 100% power converter is required. Previously only 30% power converter, but here is actually the not the doubly fed, only the stator side we use the power converter, and that is directly actually feed to the gate. And full speed, another is the wind energy, that is the this is the wound rotor synchronous generator. Previously we use the induction generator. Now the wound rotor synchronous generator is also used. You can see that there's a type 4, we actually use the permanent magnet synchronous generator mainly, but type, when we can consider type 5, that is actually we use the wound rotor synchronous generator. The 100% speed range is actually possible. So if we find out the summary of these 5 different wind energy conversion system, so type 1 turbine is actually the squirrel cage induction generator. Power converter is not required. Converter capacity is very low. That is the 0% converter capacity is required. Speed range is only the 1%. Soft starter is required. Gearbox is required, but MPTT is not possible. Maximum power, because this is the fixed speed. So the depending of the speed range, you cannot change your power flow. So this is always actually convert to the fixed power and fixed speed. Okay, because if the speed is fixed, so your power is also fixed. So MPTT is not possible. Another is actually the if any type of the fault is occur in the system, so there is no fault right through capability. Fault right through means if any type of the fault is occur in your system, the system itself actually withstand the fault. That is not disconnect from the system. But if type 1, type 2, if any type of the fault is occurred in the system, they will be disconnect from the gate. This is also the disadvantage is there. So that is actually hamper the stability of the overall gate system. Up to from the type 3 onwards, the fault right through capability is there. But type 1 and type 2, the fault right to capability is actually the not there. If you use the external circuit, okay, they will fault right to capability, but their fault right to capability is very low. So if any type of the fault is occurred in the system, so the total wind turbine is actually disconnect from the gate, which actually hampered the gate stability. So that point of view, this is the main disadvantage of the type 1 and type 2 wind turbine system. But mainly we use the doubly fed induction generator wind turbine. Here the two different types of power converter is there. We actually discuss the details. 30% converter capacity is also there. No, means the 30% plus minus power we actually change from your system. The MPDT capability is there. Also, this is the high mature technology is actually we use for the our cases, means that we use our fault right to capability. Okay. Now type 4, and when you use the type 4 and type 5 turbine, this is the high power zone. Actually, type 4 and type 5, when we use the type 4 and the type 5, this is the emerging technique. Now and mature technique is we actually use for the system. Previously 85% power we actually produce from the type 3 turbine. Okay, but the nowadays actually type main advantage is actually 100% converter capacity is possible. So nowadays actually we can use for the type 4 and type 5 wind turbine permanent magnet synchronous permanent magnet synchronous generator or wound rotate synchronous generator. because their technology is very high technology we actually use for the system, and as well as there is very smooth fall right through capability is also there.
Sir, sorry to interrupt you. Can I ask you a question, sir?
Yes.
Sir, you are showing that wound rotor synchronous generator, that is WRSG in type 4 as well as in type 5 also. In the
Yeah.
previous slide.
Uh-huh.
In the previous slide, you are showing in the classification WRSG is coming under type 4 and WRSG also coming under type 5. It's a
Okay.
summary of 5 types of WECS. Go to the page.
This one, this is the type.
No, sir. Go to the summary of 5 type of WECS.
Okay. Hey, here. Okay.
This one. In the type 4, you are showing WRSG, as well as you are showing in the type 5 also WRSG.
This is the stage. You can see that the geared stage, when we actually use this is the 3 this is because when you actually use the type 5 wound rotor synchronous generator, this is either you can use the type 4 permanent magnet synchronous generator and wound rotor synchronous generator. Because the type 4 and type 5 turbine, we mainly use the capacity of your wind turbine. Suppose you can use the more than the you understand this thing. When you use the 5 megawatt wind energy system, okay, if we install the 5 megawatt wind energy system, so there we use the W-phase induction generator and the permanent magnet synchronous generator. But beyond that, if we use, so at that time these two systems is actually failed. There we actually consider the wound rotor synchronous generator we mainly use in the system. But this system is not so much mature. Actually, there is the wind node system. There are 100% capacity is there. Depending on your converter capacity, we actually divide the type turbine. Okay, 0%, 10%, 30%, 100%, and 100%. That point of the view, permanent magnet synchronous generator wound rotor type 4 turbine, we actually use both the permanent magnet synchronous generator as a wound rotor synchronous generator, and type 5 turbine we only use the wound rotor synchronous generator. This is clear to you? Hello?
Yes, sir. Thank you. Thank you, sir. Hello? Thank you, sir.
Okay. Now you can see that we mainly concept now 85% we already talked to the 85% power we actually take from our W-phase induction generator. Okay, the 85% power we actually take from the W-phase induction generator. So today I just discuss about the W-phase induction. What is the W-phase induction generator and what is the basic structure of the W-phase induction generator? This is you can see that why it is called the W-phase. Two way we actually fed to your generator. One is actually directly connected to the stator, is directly connected to the gate. Another is actually rotor will be actually connected to the back to converter. Okay, this is, you can see that the rotor is actually, one is depending on your speed of the system, either this is used as a rectifier or inverter. Both these the power converter is actually act as a rectifier or the converter. So this is, you can see that this is structure of the wind turbine. So this is the pitch angle control. Now we discuss what is the pitch angle control. Later we actually consider the pitch angle controller we discuss. You can see what is the different of the controller is there. So one is actually the pitch angle controller is required. Another is actually the W-phase induction generator. This is the rotor side converter is there, gate side controller, and this is the AC filter is there. Gate side controller is actually mainly used for the maintain the voltage in the gate. So this is, you can see that there is no reactive power controller in our wind W-phase induction generator is there. So if we maintain the voltage level, we actually mainly considered about your gate side converter side, and inverter side controller we actually mainly control for our active power control. The active power controller we actually use for our inverter side. Inverter side controller mean this side actually. What is actually the rotor side? This is the gate side converter, and this is the rotor side converter. The rotor side converter mainly we use for the rotor side converter we mainly use for the converter. Mean which actually the rotor side converter, that is actually going to active power control system. Now we actually consider the now what is actually the, you can see that wind turbine use, when the wind turbine use doubly fed induction consisting of the, this is actually the theory part, one rotor induction generator and the AC, this is the IGBT based controller system is there. The stator winding is connected directly to the gate. You can see that the stator winding is directly connected to the gate, while the rotor side is actually connected the variable frequency through the AC to DC and AC converter. You can see that there is a stator rotor side. This is actually directly connected to the, so AC to DC and DC to AC. So AC to DC, this is actually, you can see that the way first the inverter, then this is actually you can use the rectifier as circuit, and the all the depending of the your system we actually use the controller. But mainly we DC voltage. If there is the no power is flow to the system, we, our main aim is that how actually maintain that this is the VDC voltage in the system. So this is the operating principle of the WFET induction generator. So three different condition is there in the rotor side. Either this is use the above the synchronous speed, below the synchronous speed, and the synchronous speed. If the system is rotate above the synchronous speed, for how this is actually possible to the above the synchronous speed? Anybody? Which condition the above the synchronous speed? How this is possible? System is rotate to the above the synchronous speed. Anybody?
Perhaps when the load is capacitive, perhaps
Load is
capacitive.
Load is capacity. Actually, this is not depending on the load of the system. This is actually the depending of the wind speed. Actually, the sometimes the wind speed is actually more than the your rated speed. So the at that time you can actually, what is actually generating mode. You understand this thing? That is the what is the, you if you see that the your generator structure. If you see that the structure, you can say the wind turbine, then the gearbox, and then the wind generator. So the wind turbine, depending on the wind speed, you understand this thing. The gearbox speed is also changes, and that is actually fit to the your wind generator. You understood this thing? This is not depend on the load. This is actually
Yes.
depend on the your wind speed of the system.
Yes, sir. Yes, sir. Yes.
Now, operating means above the synchronous speed in the generating mode, the rotor side converter operated at that time. You understand this thing? There is the two way. This is the bidirectional power is flow to the rotor side. If the your this is system is operated more than the synchronous speed, the power is flow from the rotor side to the your grid side. So you can understand this thing. This is the power is actually the flow from the your rotor side to the grid side. So at that time, the rotor side converter, I mean the AC to DC. You understand this thing? This power is actually supplied from the this side, C rotor. That time, this is actually converter operated as a rectifier. This is actually the rotor side. This is actually a rectifier, and the stator side is actually act as a inverter side. That is the slip power is returned to the stator. That is the power is actually feed to the system. But when the below the synchronous speed, just opposite is the power is actually flow from the opposite side, give to the rotor. Okay, when the below the synchronous speed of the generating mode, the rotor side converter operated at that time the power mean that this side the power is now flow from the this side, operated as an inverter, and the stator side is converted as a rectifier. When the slip power is supplied to the rotor, that is the bidirectional power is actually flow from the this is the converter side, and when the slip power is supplied to the rotor. And for the super synchronous speed, or the you can see the operation, PR is the transmit to the DC bar capacitor and tends to rise to the DC voltage. For the sub synchronous speed operation, PR is taken out for the DC bar capacitor and tend to decrease the DC voltage. So during the normal steady state condition, the PR is equal to PGC. The VDC voltage is the constant. Normal operating condition, if you understand the normal operating condition, your PR and PGC at the steady state condition, your PR is equal to PGC. At that time, VDC is constant. But if the any speed is changes, other is parameter is changes, that is actually effect in our VDC. So the maintain the our VDC voltage is the main task in the our the WFET induction. So what is the different of the controller we use? So that is actually the main task is to maintain the VDC voltage. So Seagate, this is actually the what is the different? We actually not understood. You can see that this is the phase sequence AC voltage generator C rotor positive subsynchronous, and C rotor and C gate as capable generator absorbing reactive power could be control the reactive power voltage of the gate terminal. Just one words you can you understand this. You will see the C gate. What is actually the C gate? That the converter side that is maintain the our terminal voltage, and C rotor the converter rotor side that is actually the maintain the our active power flow to the your system. Now, what are the advantage of the WFET induction generator and what are the disadvantage? The advantage of the systems include the low losses, which ensure the high overall efficiency and outstanding availability of the due to the compact design with the minimum number of components. Significant reduce the power rating and the cost of the converter. Only the 30% power is actually rating is possible. So the rating is only the 30% of the your main power rating. What is the actual rating of the your generator? Only 30% converter rating, because this is the your converter is actually you can put into the your rotor side. Okay, this is actually the rotor side. So only 30% power rating is required for the converter side. Only possible speed regulation or optimal utilization of energy is only 20% to 25%. The subsynchronous and super synchronous operation is possible. But the disadvantage is the slip rings, wear and tear in maintenance. Complex controller is required, and the direct connection to the grid is somewhat difficult because the stator winding is actually directly connected to the grid system. So any type of the fault is occur. So if the your fault drive through capability is not properly working, so the whole current is actually flow to the your wind energy system, that is the grid system. So that is the main disadvantage of the WFET induction generator, and the output voltage is depend on the rotor speed and the stator. Now we actually go through the main task of the any when actually we can consider the wind energy or conversion system or any renewable energy system, either this is solar or wind. Main is the how we actually take the maximum power we taking from the system. In the how what is actually the maximum power, how actually can got is the maximum power from the system. So we actually little bit understand about the what is actually the maximum power taking methods for the wind energy conversion system. So depending on the wind speed, total wind energy we actually defined by the 4 different regions. Okay, you can understand this thing that you can see that the x-axis and y-axis. X-axis we actually use the wind speed, and the y-axis we actually can consider the total power. That is actually mechanical power, or you can consider what is the total power output of the your system. So depending on the wind speed, we actually use the 4 regions. Region 1, that is actually the below the cut. You can actually understand when I actually go through the wind energy, there is the 3 different terminology is there. Cut in, cut out speed. Cut in means actually the below the your rated below the your cut in speed. Mean the if the your wind energy system is operating, if the wind speed is the 3 meter to 4 meter in the Indian scenario, so we actually not generate any power. So below the 4 meter wind speed, we actually use the cut-in. After 4 meter per second, if the wind speed is the more than the 4 meter per second, then the your wind generation is possible. Otherwise, this system is actually considered as the region 1. So there is no wind, no power will be actually produced from the your wind turbine system. That is the region 1. Region 2 is actually after the 4 to 13 meter. That is the rated meter. I can consider only the Indian scenario. So this is actually the up to the 4 to 13 meter per second. So that is actually we use the region 2. So in these cases, your wind power is actually we generate, and the maximum power taking is possible. After that, the region 3. What is actually region 3? Region 3 is actually we use the V rated or cutout speed. Now, previous cases you can see that the pitch angle controller is there. So this region 3, the pitch angle controller is actually what? If the your wind speed is more than the rated speed, your pitch angle controller is maintain the speed of the system. If the speed is more than the cutout, in Indian scenario, if the 18-meter cutout speed is actually 18 to 24, if your speed is up to 13-meter, I can say the 13-meter your rated speed and cutout speed is actually the 18-meter. So 13 to 8 meter is the region 3. So at that time, the pitch angle is actually came into the picture. But if the speed is more than the 8 meter, so that is the region 4. So there we actually stop our wind turbine. So you understood this thing that there is the 4, depending on the wind speed, there is the 4 different region is there. But when we consider the MPTT algorithm, only the region 2 MPTT controller is possible. So if your speed is actually the 8 up to the 4 meter per second up to the 13 meter, but the optimal speed, if we consider in the Indian scenario, that is the 8 to 13 meter, because this is the VWN is actually the after the 4 meter your system will generate, but the maximum speed range we actually consider the 8 to 13 meter. That is our main operating region in the wind energy system. So depending on the wind speed, we actually divide the total wind power, actually the 4 different region, first and fourth region. So below the VWN mean the cut in and cut out speed respectively. So their turbine should be stopped and disconnect from the gate and prevent it from the deviation from the generator. You understood this thing? First and fourth region, there is the no power will be produced, because the first region due to the low speed and region 4 due to the high speed. So there no wind will be produced in the other system. Second region, the mainly we use the MPTT controller, that is the your VWN, that is your cut-in and the rated speed. Within that, your controller will start to operate and exert energy as much as possible to the MPTT algorithm. And third region is actually used for the rated speed to the your cutout speed. Or the restricted, actually the here the power will be produced, but MPTT controller is stopped, and this is the pitch controller came into the picture, that is actually maintain the speed. So because if you cannot use the pitch angle controller, your speed of the system will be very high. So the pitch angle is came into the picture, but the region 2, the beta is equal to, later you can see that we not use the any pitch angle controller. So here only the converter controller is actually used. Due to the converter controller, we use the maximum power taken, but region 3 we use the pitch angle control action. Anybody, any question is there up to this? Everybody understood what is actually the maximum power point? Hello?
Sir, actually, I have a doubt, sir.
Yeah. Yes.
In the previous slide, you are showing that after 18 miles per hour of the speed of the wind, the system is not going to work. May I know why?
Hello, repeat.
Sir, initially we know that as the speed of the wind will be high, then the efficiency of the system will be high.
But this is actually the vibration of the, you understand this thing, this is the mechanical structure is there. Okay. Yes, yes. Mechanical structure, after you can understand this thing, total wind energy conversion is not depend on only the speed of that. This is the mechanical structure. After when the 18 meter per second to 24, you understand this thing. So at that time, you're
exactly. There is a confusion that M stands for miles or meter.
Meter.
Okay. Then it is okay, sir. Thank you.
Meter per second, not the miles. Meter per second.
Okay. Thank you, sir.
I repeat. This is the 4 meter per second. Okay. This is the VWN is the 4 meter per second. V rated is,
I got it.
12 meter per second, and VW is the 18 meter per second. Okay, not the mile. Okay, meter per second.
Okay.
Now, depending of the according to the maximum MPTT controller, what is the difference of the MPTT controller we use? So there is the two type of the actually we divide the two type. One is the indirect power controller. That is you see that the two type is there. One is actually the mechanical power, another is the electrical power. When you actually consider the wind power system, you consider the first the aerodynamics, then the mechanical power, then the electrical power. So we actually divide the two parts. One is actually the electrical indirect power controller IPC, and another is actually the direct power controller system. Actually, there is no, in the literature, this thing is not there. I have actually published one paper. You can, if you go through my Google Scholar, you can see that this paper there we actually divided depending of the our different of the MPTT controller. When I go through the literature survey, we see that the total MPTT control we divided the two part. One is actually maximum capture the mechanical wind power. Another is actually direct power control action. You understand this thing? So the total MPTT controller we actually divide that. What is the different of the from the literature? What is different of the MPTT controller? We divide the two part. One is actually the mechanical. You can optimize on the mechanical side point of the view. Another is actually you can consider the electrical point of the view. That point of view we actually consider indirect power controller. Another is actually considered the direct power controller in the system. Now, when we actually consider the direct power, you can see that that is the electrical power output. That is actually depend on the efficiency of the generator and the converter efficiency. But the output, that is the what is the grid power. You understand? One is actually mechanical power. That is we actually consider P wind, and the what is the P naught? That is actually the you can inject the power to the grid. That P naught we actually use the NG NC P naught. So NG and NC is the generator and the converter efficiency. That efficiency is actually reduce the efficiency of the P wind. So the P naught, if you optimize the P naught, that is actually you can consider direct power controller. That is we actually control the our converter point of the view. But indirect power controller, we actually mainly the torque control of the your system. So if we divide the total MPTT controller, indirect power control is the tip speed ratio, optimal torque control, and the power signal feedback control. Direct power control is actually the different type of the controller is there. Different method is there. If you go to the literature, there is actually see that incremental conductance, optimal relation base, hybrid approach, hill clamp set. Other algorithm nowadays actually we use the fuzzy system neural network with the when you can consider the we use the machine learning algorithm. Actually different the machine learning optimized algorithm we actually use for the MPTT controller action, because here the ML also we use for the so fuzzy system neural network adaptive multivariable pattern approach we use. So the total algorithm if we consider this is the all different way for the we actually only discuss this 5 parts. So we actually discuss from the MPTT controller T speed ratio, optimal torque. This is actually directly we control from the mechanical side. When you can consider direct power control, that is actually mainly consists about the electrical point of the view, and other algorithm actually hybrid approach we use either the electrical side or the mechanical side point of the view. Now, if we consider modeling of the system, which parameter we actually when any optimized problem, maximum power point optimize. This is one type of the optimized problem. Mean the how we actually got the maximum power from the wind energy systems. So, what is the different of the variable, and which variable actually you optimize? That is the main important parameters you should know. Which parameter we actually optimize, that we actually got the maximum power. We already write down the equation. You can see that the half rho A VWQ, that is actually the wind power. This is actually the mechanical power. You can see that on the wind power point of the view. If we consider the output power, torque developed after that, that is we actually multiplication the turbine power, that is multi power coefficient. So total torque is actually PMW by omega R. That is omega R, the rotor speed in the system. The CP is defined as the this is the mathematical equation. I not go to the mathematical equation. So this is actually depend on the lambda and the beta. Beta is the pitch angle control. But you can understand this thing when we actually consider mainly the beta is actually you can consider as a 0. Type 2 regions, so we actually mainly consider the beta. We are not use any beta. You use the beta control no such, because your power coefficient is actually the function of the lambda and beta. Beta is actually the pitch angle, but mainly we use the beta is equal to 0. And the T speed ratio of the wind turbine is actually defined by the hello. you can see that the T speed ratio, when you can consider the speed ratio, that is the lambda W, that is actually depend on the omega R and the VW. You can, the RW is actually fixed. R is actually the, what is the ratio of the system, that is you can fix. So only depend on the your wind speed as well as the omega R. You understand the rotor speed and the VW. So our main aim is that if we find out the optimal speed, you understand, if we find out the optimal CPW, so you can either you can optimize your rotor speed, and this is the VW is not in your hand. You understood my point. VW is not, wind speed is not in your hand. RW is fixed, so that you can optimal your speed ratio. If we change the omega R, optimal omega R, that is the optimal rotor speed. So maximum power we can actually transfer if we consider, if you change the your rotor speed respect to the VW, means the particular wind speed. If you optimal the your omega R, so you can got the maximum power. So this is the mathematical total the simulation diagram of the system. So how actually can represent in the PW. You can see that this is a dynamic model of the wind turbine. So you can see that the input is the VW, RW, and you can see that this is the air density. That is actually the VW is actually the your speed of the machine. RW is the input. This is the fixed rho. So this is the input, and what is the output in a system? That is the omega R. You can see that the when we write down the equation on the this system, you can, what is this equation? Anybody? What is called this equation? Anybody? In the electrical system, what is actually called this equation? D omega by dt 1 by t. What is called this equation? Anybody? Any not the wind system, any our electrical system, power system, what is called this equation? This is mechanical power minus electrical power. Anybody? You know the swing equation? Hello?
Yes, sir. Yes, sir.
This is actually the, from the swing equation we actually find out the
Okay, okay.
this is. So you can see that when you actually go to the problem formulation of the MPPT controller, this is the depend on the turbine output power depends upon the CP, rho, and the turbine parameters. But you can see that the air density and the turbine parameters are constant value. We not change the system. For a fixed pitch angle control, the output power is mainly depend on the value of the CP. So you can see that the EP maximum, you can EP change the maximum power coefficient. So you got the maximum power from the your system. So our main aim is that we actually find out the T speed optimal T speed ratio at that time, how actually got the maximum power of the your system. So this is the CP is depend on the rotor speed of the wind turbine. So the when we actually consider the maximum power transfer theorem, our main aim is that how we actually optimize the omega R, that is the rotor speed. We actually optimize the rotor speed in the system. So this is the different type of the optimal speed. You can understand this. This is the different type of the algorithm is there. IPC. You can see that this is the when you can consider the indirect power converter system MPT controller. T speed ratio is the first method. So you can see that the T speed is actually we can consider the R omega m into the VW. Here the R and VW is the we not change the R magnitude and the VW. We only optimal the omega m optimal. So if we change the omega m optimal, so maximum optimal value, if we rotate the your system, your lambda will be actually run into the omega. Lambda is actually run into the optimal speed, and depending of that, you can actually got the maximum power from your system. So this is the different type methods is there. We actually not go to the details of that. So this is the optimal torque controller of the system. So this is the torque controller of the optimal generator. TM is actually consider that if depending of the this system, this is the same. We actually use the omega AM. We actually consider the lambda optimal. We actually consider, and then we actually got this system. This is the total block diagram of the system. So how actually can implement the your MPDT control system. This is the power signal feedback MPDT controller. I just go through the what is the different the MPDT controller is there. The details if you want, so you can go through the one. My paper is there, so there is the details is actually there. So this is the direct method. So Hill-Cam search algorithm is there. Incremental conductance approach is there. This is the now the hybrid approach. Is I not both. Later we actually one methods we actually just discuss how actually can implement actually. This is the multivariable optimal technique. Now, how this optimization technique, if you use the artificial bee colony, how actually can implement? Mean the in the this is our main task is the from the wind speed, how actually got the maximum power from the your system. That is our main aim. So this is one type of the optimization problem in the power system. You understand this thing? Our main aim is that how actually can optimally you can find out the omega r, and how actually you can find out the maximum mean the omega, how actually you can optimize the omega. So that point of the we actually find out the maximum power from the system. Anybody any idea about the artificial bee colony ABC algorithm? Any student any idea is there how this is working? Anybody? This algorithm, anybody? Any optimized algorithm, you know, genetic algorithm, swarm optimize. Hello?
No, sir.
Okay, just I discuss about the, this is the algorithm is actually there, the ABCC, artificial bee colony algorithm is there. So what is actually the background of this? What is actually just like a, this is actually the colony honey bees actually categorized into the three. This is actually the different algorithm in the how the honey will actually bee actually collect the honey from the your system. So you can see that there is the three different type of the group is there. One is the employed bee, on-hooker bees, and the squatter bees. So initially, all the bees are currently associated with the searching the food sources. Okay, are called the employed bees. Mean this is actually the one type of the optimized technique. Optimized technique means that there is different of the bees there, so they will be actually searching the honey actually their food. So this is the three different member is there. So that there is the initially we actually consider the three different bee is there. Depending of that, all collected the honey that come back into the heaps and store the honey, starting the weekly dance and sharing the bees. So this is the one type of the bee is there. They will be actually collect the information. One type of the bees actually just collect the information and they will be find out what is the most suitable position. Okay. Another type of the bees is actually there. They will be actually find out the what is the optimal solution of the system. This type of the concept we actually apply it in the our cases. Okay. So this is actually hello. This thing is actually visible, everybody.
Yes, sir.
Okay. So for the any optimized technique, so we actually use the when you can consider genetic, we use the number of iteration is actually required. So the population of the bees is actually required. Maximum cycle number we actually use, that is the your input from your system, and number of tiles and objective function. The whole forging process at the cycle is categorized in the four different phases: initialize, employed, onlooker, and the Scott phases. This is actually use the you understand this thing when you actually we use the bee colony actually when you use the artificial bee colony. So they are actually their concept. There is the three different type of the bees there. The employer bee is actually the searching the honey actually. All the bees actually searching the honey in the system. So that part of the bees actually we can consider that they are the employed actually, employed bees. Onlooker bees actually they will be bees are the assigned to collect the information. Onlooker bees actually they collect the information of the systems, and they will be find out the what is the optimal value actually. Optimal value means actually they will see that the what is actually the collect the information which information is more suitable, and if there is the value is the not the suitable from the your system, so another phase is there, the squad phase, they will be again start the system. In the optimized technique here, one is the first we actually initialize the phase. We don't know the your this system is actually the what is the optimal value of the system, so we actually consider the within the maximum and the minimum value. You understood this thing. In our cases, what is the our wind speed we actually know the 8 to within the 8 is actually our cutting speed, and what is the rated speed, that is the our the 12. So within these ranges, you understand this thing, 4 meter to 12 meter, within that range we actually find out the what is the optimal position of the our wind turbine. So we know the maximum value and the minimum value. Within that range, we actually find out the what is our rotor speed. So maximum minimum value is required. Any optimization value when we actually see we actually within the range we actually find out the system. So that is the first range. We actually use the minimum and the maximum bounds of the your system. So we actually this is the algorithm of the system. So first algorithm is actually we use the arbitrary SPQ, mean the we find out the any arbitrary value of the P and Q. You understand this thing? Any arbitrary value of the P and Q, we actually find out the what is the optimal of the SP. But this is not the optimal. That is actually find out the first iteration value of the system. That is we actually represent every cycle. What is actually we can find out the X value. That value we actually represent into the your generated new solution. That is we actually represent by the VPQ. Out of this is the n number of what is the maximum cycle we already considered, m cycle, maximum number of cycle we already considered. So every cycle we actually got one x value, mean the one optimal value. Within this optimal value we every you understand every cycle we got the one x value, but this is how actually you can find out this is the optimal value or not. So that is actually we can consider the maximum fitness value of the system. So we from the fitness we actually put the your depending of the your VPQ. So we actually use the your one fitness function is there. So there we actually put the fitness function, and depending of that we actually find out the what is the base fitness function in the system. So if the your n number of cycle is there, so we actually use the n number of different value. Within this m number we actually find out the what is the optimal value, and within that value we actually take the next cycle the initial value of the system, and this way the your total system will be actually going on. Now how we actually use this thing is our MPTT controller. Your aim is the MPTT controller is that is the power speed card, that is what is actually show the different region. So within that regions we actually find out the what is the optimal rotor speed in the system. You can see that our first optimal what is actually find out the equation. There we actually show that the what is the omega r maximum and omega r minimum. We choose the total population of the bee is the 60, number of food source is the 30. This is actually choose the arbitrary initially how many population is required. Depending of the your system you can actually choose it, okay. And maximum cycle number we actually use the 60. So this is actually we use the maximum and the minimum value. So maximum minimum value you should know what is the your range. Within that range we actually find out the what is your optimal value. So the output power of the wind turbine PM is the selected the fitness. So this is your optimized PM. So what is your omega r, depending of that we actually put the omega. You can see that. So what is our wind power equation, what is the optimal value we actually can occur from the equation number 11 12, that we actually put our power equation, and that power equation we actually found out what is the optimal power we actually got from the system. So if the your 60 number of equation is 60 number of your population be the your 60 equation you actually got 60 different optimal values you can got from the your system, and within the 60 value you can find out the, what is the your optimal solution of the your system. So this is the algorithm we actually consider. The ABC algorithm is that there. So initially data enter the power system data and the algorithm parameter is there. So randomize the initial solution, calculate the fitness of the solution. Fitness of the solution is actually depend on the what is the actually your objective. Here the objective is actually the optimal the power flow to the your system. So that point of the view, when you actually find the optimal flow of the optimal power flow, so there we actually use the our fitness function. So randomize the initial solution, we actually use the random value, but after that we actually every initial value we actually calculate the fitness solution. Fitness solution we actually calculate after the you can find out the every initial value we actually find out the what is the your fitness function. Then we actually searching on the old solution, calculate the fitness of the solution again, because this is the new value. And after if this is actually not the suitable of the PBR, if the this system is actually improvement, so this we actually consider the again mean that initially the employed bees is there, then the you can understand this thing, then the onlooker bees, then the squad bees. So these the 3% we actually find out. Initially we find out the arbitrary, then we actually consider the onlooker bees, mean the what is the optimal solution. If the optimal solution is actually within the range, so then we actually stop. Otherwise we actually again go to the squad bits, we actually find out the what is the next solution of the your system. So this way we actually go to the up to the maximum cycle. Okay, so if the all the cycle is completed, we actually find out the what is the display of the final solution of the system. So here we actually can give the some we actually go to the two range we actually consider, because the we find out the wind depending on the wind speed, we actually find out the what is the optimal position. So here either you can actually we use the you can see that the our wind speed between the 3 meter to 11 meter, because we say that the within this range we actually find out the optimal value of what is the your optimal solution of the system. So arbitrary we generate. One is actually the we generate the wind speed, mean that we simulate the wind speed and then we actually find out the optimal speed. Another we actually use the real world data. We take the real world data and then we actually find out the solution of the system. So this is actually the different type of the parameters. We use the W5 induction generator. This is actually the rated power. You can see that the when you can generate this is actually you can find out what is the rated power of the system, and you can see that after the simulation of the system, our main aim is that the how actually you can consider actual power output, and through the optimized technique we actually find out the power will be actually match or this system. In the every point we actually through the optimized technique we collect data the system, the power output ABC and actual output power. So so this is actually match from the our optimal optimization techniques. This is the we actually use the different of the ABC the partial swarm optimization techniques in there. This is another technique, the hill climb such optimized techniques. So this is the different of the simulation results we actually got, and we actually see that the ABC is the most suitable than the our partial swarm optimization and the hill climb such algorithm. So any optimized problem when we actually consider this is actually you can also compare with the this result we actually satisfy the our statistical methods, mean the mean absolute error, root mean square error, mean the how the coefficient will be actually coming into the system. So ABC system is more suitable than the other type, mean the error from the error point of the view. This is actually more suitable than the other variables. So if we summarize this system actually, so ABC optimized technique has been designed for the maximum power point tagging. So So we two type of the selected. One is actually random selected, another real world system. And turbine power output generated using the proposed control technique found to the more similar actual power output of the system. And effective proposed algorithm in the PSO and the HS space. Actually, the main our main motto is there. So first, any type of the optimized problem or any computer oriented when you use any simulation in your problem, first you actually use the problem formulation. So mathematical expression is required. First you actually create the your mathematical formulation. You can see the which parameter we actually optimize. Depending of that, you can actually write down your objective function. Then the next task is there. So which type of the optimized value means you can different other method is there. Global optimization and the you can understand this and different type of optimization method is there. Either you can use the global optimization value and your traditional optimization method also you use. So which type of optimized methods you can actually use to the your system. This is the your second task. Then you can see that the which method is most suitable. There is which method is most suitable in your cases. Either if the system is most nonlinear, so you can use any complex nonlinear optimization method. If the very simple linear methods in your system, so you can use the linear optimization method is in your system. Any question is there? Any question is there?
No, sir.
Anybody any question? Any? Any? Another okay 15 minutes another 10 5 to 10 minutes I just discuss about the another problem in the wind energy when you actually consider the wind energy system is there. So this is actually visible anybody?
Sir,
Yes, sir,
it's
it's
visible in
visible.
summary.
One minute. This is visible.
Yes, sir.
Yes, sir.
So another problem we actually there is small signal stability analysis of the system. Now what is actually the small signal stability in a power system? Anybody? What do you understand about the small signal stability? What do you understand about the system stability? And what is the difference between the tangent and the small signal stability? What is the main difference between these two? What is the stability problem in the power system? Anybody?
Sir, it's the ability of the power system to maintain synchronism when subject to small disturbance.
This is the small signal or tangent stability? What is actually my question is actually the how actually you can difference between the small signal stability and the tangent stability. What is the main difference between these two? Why you actually not study? What is the requirement of the small signal stability study in any electrical system? Every time we actually from the gate stability point of the view we actually study from the tangent stability. You know this is actually we can see that if you choose the our circuit breaker relay or in the system stability, we actually go through the tangent stability. But what is the requirement of the small signal stability study of any system?
Sir, good evening, sir.
Good evening.
Sir, as per my knowledge, small signal stability refers to load fluctuation that much, and transient stability refers to sudden fault occur in a line.
That one I say the tangent stability is actually required to the our gate stability point of the view. Okay, your system, suppose any fault is occurring in our say, system. So at that time, the system will be how this system will actually affect in our overall gate, or how the system will actually withstand in the from the if the any type of the fault is occur. So how system will withstand of the system. But the small signal stability is the internal stability of the your system. Suppose every time the you understand my point. Every time the load is changed in our system, so that is how this is actually affect in our overall system. Suppose either this is actually your synchronous generator, or if any type of the wind system when the renewable energy is actually connected to the system, how they will actually behave. So that point of view, the small signal stability is stability means the small disturbance. You understand this thing. If every time the load is actually changes, small load because the load is you cannot predict it. Every time the load is changes. So if any time the load is changes in your system, so how they will be actually withstand of the system. So this is the small signal stability. Now this is actually size changes. Anybody?
Yes, sir. Yes, sir. It is changing.
Now you can see that when we actually use the small signal stability study, our whole system we actually study into the state space approach. This is actually most difficult task to the small signal stability study. So first task is the small signal stability study. Our whole system we actually represent by the state space dependence of the system. So state space dependence, everybody knows. So we actually consider the x dot is equal to x plus bu form. So this form we actually represent the whole parameters, whole the system. Here, when we actually consider the wind energy system, our main task is actually how actually mathematically we actually represent into the system into the this form. So that point of the view, our main see the how many state is there when you can any small stability study. Our main aim is that how many state is there. So here the state we actually use the our rotor current. You can see that the IQS, that is actually the our overall system. Actually, you can see that the sorry. So here we actually use the our generator side. You understand this thing? Our generator side current. If you think about the total W induction generator, the stator side is there, rotor side is there, as well as the our rotor speed. So we actually consider the IDS, IQS, VQ, VD, omega R, theta, omega T, IDG, QG. That is actually the different type of the state space, and the input is the mainly the our controller input. So what is input? So the we actually consider the grid side inverter. What is the different the grid side inverter voltage? Our output is actually the torque control and the VTG and QG. We actually not go to the details about this thing. So this thing I just divide over the what is actually the basic structure of the system. So in the first there is the total 9 state variable is there. So total we actually use the 9 equation. After that we actually find out the basic structure, the state space approach is there. So any state space when we actually consider the our small signal stability study, because the tangent stability study, you know, the our well-known method is there equilibrium criteria, step by step method is there. But when we actually consider small signal stability, we mainly go through the eigenvalue and the participation factor analysis. Okay, the participation factor analysis, eigenvalue analysis means actually we see that straightforward. We actually see that the how many eigenvalues mean the how many roots in the lie on the left hand side of the S plane. So if the any roots lie on the right hand side of the S plane, we actually go just like a control system point of the view. We actually see the system will be unstable. But another factors we actually use for the small signal, that is the participation factor analysis. The participation factor analysis, anybody any idea about the participation factor? The participation factor is actually used how the your contribution of the different state in the eigenvalues. You understand this thing? There is the two type of the system is actually there. One is actually we can consider the eigenvalues. Another we actually consider the state variables. Suppose the every state, suppose the you understand this thing, every eigenvalues, how they will be actually contribute the number of states. So depending of that, we actually find out the state space dependence. So I not go through the details about this thing. So there is the different of the state space dependence is there. Just I can give the overview. So if you any type of go through the any research or otherwise, so you understood in there this term you actually consider. So first any small signal stability study, first thing is actually you can represent by the state space dependence of the system. Depending of the state space, you can actually find out the eigenvalues. After you can find out the eigenvalues, we actually go to the participation factor analysis. From the participation factor analysis, we actually see that the what is the different state is actually here you can actually see the different modes and the different state. So we actually see that the how the different state is actually significance of the different mode, and depending of that we actually find out the your system will be stable or unstable. So this is actually different impact of the system. We actually not go to the details about this thing. So this is actually the eigenvalue analysis. We actually use the what is different type of the modes of the system, and then we actually find out the what is the different of the stability study. Okay, thank you. So if any question is there, basic question you can ask to me. Okay, any type of the question you can actually if on the related to or any power system question, if you any you want you ask to me. Actually I just give the overview, I not go to the details about this thing, because if this is not possible to go to the details of the system, I just give the one overview. So when you actually consider the small signal stability maximum part tracking system, so what is the different of the methods is there, so how actually you can calculate the system, what is actually the wind energy system, what is the different type of the phenomena, so that I give the overview. So anybody any question is there?
All the participants are requested, if any questions is there, you may ask here. Sir is there. Any questions or any doubt regarding the power system and its stability analysis or regarding any optimization? Sir, I think they don't have any doubt.
Okay.
Prasantini madam, you may conclude the session.
Yes, ma'am. Thank you so much, sir. Thank you, sir. Thank you, sir, for such a highly insightful and enriching session on mathematical modeling of complete wind energy system. And your valuable knowledge and experience have truly deepened our understanding. Thank you, sir. And on the behalf of organizer and all the participants, I extend my gratitude to you for spending your valuable time and sharing such valuable knowledge with us. Thank you, sir. Thank you once again for being with us today and making this session truly remarkable. Thank you, sir.
Thank you everybody.
Sir,
Thank you, sir.
Dr.
Sir,
Kalyan, sir, we want to take a photograph. Please stay.
We also request all the participants to please switch on your cameras for a few minutes so that we can take a group photograph to capture today's session.
Sir, can you remove this slide?
Okay.
Okay, thank you so much, sir.
Okay. Thank you,
Thank you,
everybody.
sir.
Okay, sir.
Dear participant, we now request you to kindly fill out the feedback form for this session. Already, I think feedback is already shared in the chat box. And this is very important for us and also required for AICT records. Kindly do that as soon as possible so that we can start our next session. Already time is already 7:30.
Prasantini madam,
Yes, ma'am.
Dr. Debasis Chatterjee has joined us already.
Already, na?
So,
Okay, okay. Sir, good evening, sir. Good evening, sir, and dear participant. Due to some unavoidable circumstances, engineer Satwik Swain will not be able to join us today. We are, however, truly honored to have with us Professor Dr. Debasis Chatterjee, sir, professor in the Department of Electrical
one second,
Engineering.
madam, 1 second. Let me confirm because sir has joined. Maybe he has left or what. One
Okay,
second.
okay. Yes, yes. You confirm me, then I will start.
Uh-huh.
Madam, good
Sir,
evening. What about the attendance of this session?
attendance already share.
In
Uh,
which one? WhatsApp group or in this chat?
attendance tracker is there. We will take it. Don't worry. So, Prasantini madam, Debasis sir has already joined. You can continue this.
Okay. Good evening, sir.
Good evening. Good evening.
Good evening, sir. Sir, on the behalf of organizing committee, I extend our heartfelt gratitude to you, sir, for instantly stepping in and will delivering the session on harnessing wind power integrated with microgrid. Sir, we deeply appreciate your graciousness for accepting our request at short span of time and agree to share your vast knowledge and experience with us. Your valuable insight will truly enrich today's proceedings and provide great learning to all the participants. So, Professor Dr. Debasis Chatterjee received his BE degree in electrical engineering from Yadavpur University, Kolkata in 1990, followed by an MTech degree from IIT Kharagpur in 1992 and PhD from Yadavpur University at the year 2005. From 1992 to 2002, he served as a senior design engineer with Nelco Tata and Crompton Greaves Private Limited, Mumbai, specializing in industrial drives and automation. He also worked as an assistant manager at Philips India Limited in lighting and electronics design. In 2002, he joined the Department of Electrical Engineering at Yadavpur University, where he has been serving as a professor since 2012. He also pursued a brief postdoctoral study as a scientist at the Technical University of Germany in 2005 under TICUB scheme. Professor Chatterjee has an impressive academic record, having published over 110 international journal papers, including IEEE, IET, Elsevier, and Taylor Francis, and more than 70 international conference papers. He has supervised 18 PhD theses with 6 ongoing and guided over 40 master theses. His excellence in research has been recognized globally as he has been constantly listed among the top 2% scientists in the world, as per Stanford University prestigious database. His research interests span electrical circuit, electrical machine, variable speed drives, electric vehicle, renewable energy generation, and power quality studies. Professor Chatterjee's academic rigor, industrial experience, and research make him an eminent expert as a source of inspiration for student researchers as well as professionals. Let us warmly welcome Professor Debasis Chatterjee, sir. Sir, this is your session. Now you can start.
Okay, first of all, thank you all for arranging some seminars and selecting such topics which are really relevant and which can help people to interact, and this can be a subject for next 10-15 years at least. So the topic what we have selected. So thank you all, and thank you to all the participants also. So I'm just starting to share my slides. So we will have some interaction with you for the next 1.5 hours or so. So let us see that. So is my screen visible?
Yes, sir.
Okay. So good evening to all of you. So this session we will just learn that how wind power is harnessed and usually harnessed, and it is integrated with microgrid, and along with some role of computational intelligence, means where we can use computational intelligence in doing that, right? Now, first of all, why wind power, why renewable sources, that you all know actually. I'm not going to repeat everything, but you all know that there are many renewable sources, isn't it? So these are the listed renewable sources which are normally found in literatures as well as in practical applications, like say wind, solar photovoltaic, micro hydro, tidal, geothermal, fuel cell, biomass, etc. Now, out of which, if you see, the share of power among the renewable energy sources, or the share of energy that is actually mainly used for grid integration or usage for, say, human civilization, are the top three: wind, hydropower, and solar photovoltaic. Because you see, the availability of these three energy sources are more, comparatively much more compared to the other sources what we have said, like say tidal. Tidal is there, but still conversion facilities are a little bit limited due to different reasons. Geothermal, fuel cell, biomass. Convenience also, wind, solar photovoltaic, micro hydro, convenience wise also they are much ahead compared to the other sources. Now you see, these renewable sources have some inherent difficulty. Inherent difficulty means, suppose in a conventional plant, supposing a thermal power plant is giving you a power of say 200 megawatt at this moment. Now, if the load demand arises, right, say it requires 250 megawatt, you have the capacity, plant capacity is there, but currently due to the load of 200 megawatt, it was generating 200 megawatt. Now suddenly the load demand increases to 250 megawatt, and you can also increase slowly your production up to 250 megawatt because you have reserve, like say coal and etc. that can be pumped in, and then turbine power can be increased, and then finally your electrical generation can increase. So, and similar is the situation for decrease also. But in case of renewable energy, there are uncertainties. Like say, you cannot predict the wind power. Say right at this moment it is 10 kilowatt. So after 10 minutes, what is going to happen? There can be high wind, there can be low wind, etc. Hydropower a little bit stable, but still it varies with say nature, it varies with seasons, it varies with different say lunar systems, etc. Now, solar photovoltaic, you also know that clouds, and also inevitably in the night time, no solar photovoltaic can be generated. Therefore, actually, these sources are uncontrollable sources from the source side, isn't it? Now, after that, you have to make it usable. Now, although people knew it from long before, but because control is difficult, so we could not produce it, right? Now, with the advent of power electronic controllers, with the advent of high power switches, high power semiconductor switches, so everything has become possible, right? So that is the reason actually nowadays more stress is given on wind power or solar power or hydropower, whatever, and that are slowly replacing the conventional sources. Now, another thing regarding these sources are that these powers are generated and then connected to the grid or interfaced with load with some controllable power electronic controllable devices like say inverters. Now the source inertia has become very less. Now this power is not very, not very comfortable to dispatch. Now the concept of local usage of this power are more. So we are actually the trend is to generate local small grids called microgrids, and nowadays even smaller smart grid and even smaller nano grid systems are coming. So those grids are actually connecting those renewable energy sources and then finally giving to the consumers. And at the same time, these microgrids or smart grids, they are also connected to the main grid system. Now, idea is to remove the loading of the main grid as much as possible, right? So this is the way the trend is going on. I mean, the generation is having a paradigm shift from the conventional towards the non-conventional, from the big grid to the micro grid to the smart grid to the nano grids, etc. Okay, so this is what. Now, if you see global scenario, as I was talking, that what about the different sources? Now we see, if you globally see in terms of gigawatts, so we find that normally these two are playing. Actually, this wind power and solar photovoltaic, this we have shown. Now up to 2020. Now later on also you will find that these two will be actually prevailing along with the hydropower, micro hydro or small hydro, etc. Now, how these energies are harnessed, first of all. Now, how this renewable sources are used to supply to the grid system. Now, here is a block diagram which I have shown you, showing that in the first block, we have a primary energy source. Right? These energy sources are actually those sources, like say wind, hydro, the solar, then you have tidal, etc. Right? Now these sources, they are uncontrollable naturally. So the power generated or these sources are interfaced to the grid through some power electronic interface. Yeah, this will be rotary and then static, or both rotary, static, sometimes only static. So in case of PV, we have only static. In case of others, we have rotary plus static, etc. So these are the power electronic interface, which is actually helping these sources to get converted into usable energy, right? Now we have grid interconnecting transformers. It can be a reactor also, etc. Now, in order to control all these things, we have certain control blocks, like say measurement block, and then control and protection block, etc. Now, in control and protection, as I am repeatedly telling, that again there is some, you can say, drastic shift, right? Drastic shift means nowadays we are having all these processors available, which are highly, which has the capacity to compute in a fast manner, and also it has the capacity to compute many signals, right? Like say digital signal processors. Now Texas Instruments and others are coming, and then already come, not coming, and then other microcontrollers like say microchip, Raspberry Pi, etc. These are all available in a smaller to a larger scale. So therefore, there has been, you can say, a revolution in this field, so that we are able to do everything. Now, whatever designing a digital PI controller is really, you can do it in 10 minutes or in half 1 hour time. But earlier, it was not possible. Okay. Thanks to VLSI techniques, and those IC chips, I mean microcontrollers, microprocessors are little lower, microcontrollers, and then digital signal processors are coming. So this is the block, basic block. Now for wind, actually there is some small sound is coming. So is it somebody's thing? I'm getting some.
Yes, Amod sir, please mute. Amod sir, please mute your speaker.
So now you see that we will see few things like, say, how it is converted. Now, as I have said in this block, there can be a rotary block or rotary plus static, etc. So we will not have the time to discuss the solar system, but really wind will see. Now the rotary system is actually this wind turbine generator combination. Wind turbine generator combination. Now, wind turbines, you know, there are different types of wind turbines available. Now, basic things are actually this horizontal axis and vertical axis wind turbines, right? And then horizontal axis wind turbines, if you see, they are the larger part of the system. Means here the ratings are larger normally, and they are you can say their installations are sometimes in the onshore, like say the land, and sometimes, and in majority times you can say the offshore, that means in the sea. And nowadays floating wind turbines have also come. So due to lack of time I have not shown you, but you can remember that floating wind is also has also come actually now. Okay, so these horizontal axis turbines, you see that they have certain blades. It is shown like we have there are blades, right? There can be different designs, maybe 3-blade system, 2-blade system, even single blade system is there, or multi-blade system. Now these turbines, they are able to nowadays you can see this second picture, I mean picture in the right side, where the shown the extended portion shown as nacelle. Now in this we have the generating system, rather the generator and other system, and behind this there are another thing in modern turbines are coming, that is have already come, that is ear. You know, ear, some arrow type thing. If you have seen in turbines, you will see some arrow type extended portion. Now these can actually rotate the entire turbine system in the direction of the wind, right? So that that wind from any direction can be converted. Otherwise, earlier it was a fixed location. Now you control the second point, you see, wind sensors to rotate tower in your direction. So that can be possible. Okay. Now these turbines are found normally with higher wind velocities, ranging from say 4 meter per second, and in kilometer, if you see 4 meter per second, you multiply by 3.6. Just you can get it. So 4 meter per second to around say maximum 20 to 25, after which we have to shut down. Okay. So these turbines, and second part is actually vertical axis wind turbines, and there are two types, Darius, Sebonius, and all. So I'm not going into those details because this is not the turbine class. So normally these turbines, where you see that generator is located at the bottom. Generator is located at the bottom. Now the turbine can rotate in any direction based on the wind. So all direction wind can be used. And this gearbox is actually helping this vertical rotation motion into horizontal rotation motion. And then the generator is rotated. So these turbines, capacity wise, they are on lower side. In the upper turbine, if you know that there can be I mean rating of around 10 megawatt per unit in one unit, 10 megawatt. Even nowadays 16 megawatt turbines are available. And for these turbines, vertical axis, they are mainly aimed for domestic applications. Even rooftop applications are possible. Now they range from very small fractional kilowatt rating, around 300 watt, to at the most say 15-20 kilowatt maximum. So average ratings here are usually from 300 watt to 1 to 1.5 kilowatt. That means very well suitable for domestic application. Okay. So now we will come to the electrical part. Now where we see that how they are generated, how the energy is generated. Now the electrical generators are actually mainly four types. One is a synchronous generator. The second one is an induction generator, which is a squirrel cage type, and the third one is another induction generator, which is actually slip ring type. And the commercial term, or you can say technical term for this generator, is known as doubly fed induction generator, DFIG. The term I think you have heard of earlier. And the fourth one is actually brushless doubly fed generators. Now, these brushless doubly fed generators, they are very new, and it's a new research. Those who are stepping into, research in wind turbines or wind energy extraction systems, they can easily find papers from these last two, the doubly fed induction generator and brushless doubly fed motors. They can do it. Now, the second, now we'll just briefly go through that what are these generators, how they, generate energy. Now, you see, synchronous generator, as an electrical engineer, you have already read it probably. Now, here the generation is, you have to give field supply, right? Field supply, which is DC, and field will rotate, right? And DC supply is given through brass and slip rings. Of course, nowadays brushless excitation system is also there. That can be there, but it requires certain other hardwares. So this field supply is given, and then the field is rotated through a prime mover, right? The field is rotated through a prime mover, and this rotation gives the stator conductor, you can say, induced voltage, right? Because there is a rate of change of flux linkage in the stator coils, and you have a three-phase generation in the stator. So this is what the basic principle of generation. So now you see, naturally, the voltage generated at these terminals A, B, and C will depend on the speed of the turbine, right? And as well as its frequency, because you know this 120 F by P and all. So here that N is your rotational speed, 120 F by P in RPM, and then corresponding F will be generated because your pole is fixed. So now when the speed varies, your frequency varies as well as your voltage varies, right? Now when the turbine speed will change definitely, as because you know the wind speed is not a constant term. Always I'm telling you that these are very, very unpredictable sort of things. So there are all AI algorithms and certain other algorithms are actually already in vogue, or their new algorithms are coming to predict the wind generation in next hour or next 2 hours, like that. And depending on that, the pricing and the generation and then the loading on the other grids, those are actually possible. Can be predicted. You can say predicted and can be effectively implemented. So those things are different. So wind speed, the thing is that wind speed is changing, right? So when wind speed is changing, so naturally we have a variable frequency, variable voltage generation at terminals A, B, and C. Now this is of no use. You know, this AC voltage normally if you only connect to some heating loads, that is helpful. And otherwise, in some other loads where the motors are running and all, so this variable frequency, randomly variable frequency and randomly variable voltage will not really of good help. So therefore, this power is actually rectified and DC. And then it's filtered with some standard LC filter, T, pi, whatever be the configurations. And then after that, this DC voltage will be inverted, means it will be made AC phase, and then at desired frequency and desired voltage level to interface with either the load or the grid. So this is what the basic system is, okay? And it's a variable speed system, mind it, the variable speed system, but we require two devices, one is rectifier, another is inverter. Now this rectifier and inverter, when you require, its rating also has to be same as that of the rating of the alternator or the synchronous generator. So therefore, a 2 megawatt alternator will require a 2 megawatt capacity rectifier, a 2 megawatt capacity inverter. This not only, makes the system bulky, but also it adds to the cost. And design of large megawatt inverter is really, you can say cost is proportional to the square or cubic of the ratings. So naturally, cost, space, everything, as well as reliability, because more power for the inverter delivers more power, means the chance of heating of the devices are more, and the failure, failure probability also increases. So if failure probability increases, your reliability also will decrease. So this way, actually, it requires synchronization and all that thing. So this is the basic things for the synchronous generators, and pros and cons. Pros means actually it can generate at variable speed, means wind speed varying, and you will be able to generate. But the major drawback is that you require few additional converters of large ratings, and at the same time, field also will require another converter, rectifier and all you have seen. Yeah. There can be many other excitation schemes also. Now, to avoid the field variation, to avoid the, say, field converters, so another scheme which is actually, in use is actually PMSG. Instead of an externally excited SG, synchronous generator, we use PMSG, permanent magnet synchronous generator. Now, permanent magnet synchronous generator, actually, it has another inherent, difficulty is that, say, its field excitation is fixed, because permanent magnet strength is fixed, let us say. Now, this generated voltage is rectified voltage is sometimes boosted if required, or the boost converter can be avoided if it is not required, and then this fixed frequency converter, and then transformer and grid. But the situation is that, as I am telling, wind speed is widely varying. For higher wind speeds, what will happen if we take this kind of configuration with the help of diode rectifier? For higher wind speeds, the generated voltage will be large, isn't it? Because the field is fixed, wind speed is increasing, so voltage magnitude is increasing. So in the earlier scheme, we have a rectifier. So if there is a control rectifier, so for higher speeds, we can actually reduce the excitation voltage, so that my generated voltage can be controlled. So this facility is not available here for diode fed system. So normally, again, another converter is required, which is known as active front-end converter, which actually can be used to demagnetize the field at higher speeds. And this task is it's a bidirectional type of converter. It will provide the field, it will provide some excitation in the opposite direction when the wind speed is increasing above certain levels, and then the field excitation can be made constant. But again, there is a large converter, large cost, etc. All those things are coming. So this permanent magnet synchronous generators also is a good scheme under variable frequency, or rather you can say variable wind speed situation. But normally this is restricted for cost purpose, or you can say space. Not only cost, space, cooling, its reliability, etc. All these are lower. So this is what we get from, and this is the synchronous rectifier and chopper, the detailed view, the boost chopper, and then rectifier, and then inverter, like that. Now, these are features, you can say maximum power point, then control of grid side, DC link voltage, unity power factor, etc. Wind turbine control, pitch control, all those things that can be really achieved. Okay. Now, we go to induction generator. We go to induction generator. Now, induction generator, as we have said, are of two types. One is slip ring type, another is squirrel cage type. Now, first of all, we are showing the squirrel cage type. And the first scheme is shown as self-excited scheme, known as ACIG, self-excited induction generator, right? Now, how excited and self-excited, excitation and self-excitation. Now, you have seen synchronous earlier. Now, synchronous machine is a doubly excited machine. Doubly excited machine means you can say there is a separate excitation for rotor and another is the stator, right? So we can have a separate field supply, and if it is a motor, it's a separate armature supply, or if it is a generator, field supply and then armature voltage generation, right? For induction motor, there is no separate field, isn't it? So excitation comes from the stator voltage only. So self-excited means we will not use any external source for excitation. Now, how it is done? Now, it is connected to with some stator is connected with some capacitors. It may be star or delta, depending on the choice or depending on the amount of capacitors available. All those details I am not going. Now, these capacitors will supply the reactive power. It is shown here. Q is flown from the capacitor, and it comes to the induction generator, and this reactive power helps to establish the flux inside the machine. And then prime mover will be a turbine, wind turbine, so active power will be generated and it will be coming to load, right? Now it is not shown in grid. Why? As because you know, here it is a variable frequency generation, variable speed system. Now the overall voltage generated at these terminals, they are of variable frequency, variable voltage nature, just like synchronous generator or alternator at variable speed we have seen, right? Now, you see here, this is the equivalent circuit. The method of excitation is like this. So due to the rotor, you can say residual magnetism, when it rotates, so there is some small voltage generated at the stator terminals. Now, when the stator terminals have some small voltage, so this some current will flow through the capacitor, right? Now, the capacitor current, you know, leads the voltage by 90 degree, and the field excitation current, which is actually the inductive current, lags it by 90 degree. That means you can assume that this current, capacitive current, is supplying the inductive current. Okay, that means the excitation is generated from the capacitor itself. So that is why it is termed as self-excited induction generator, ACIG. Now, this is the this you will see later. So this is now the voltage is generated, voltage and frequency, and it is connected to those loads which are able to absorb this, you can say, variable frequency, variable voltage supply. Normally heating loads. Okay. Otherwise, you have to again rectify it and then invert it to make it usable for standard power supplies, like the motor supplies, like the grid systems, etc. So these are not used in bulk. These are all small generators of fractional kilowatt to few kilowatt ranges, and mainly for domestic or experimental applications. Okay. So now here comes the other one, the same self-excited, the same squirrel cage type of generator, which is connected to grid, right? Now the grid interconnected system, you know, that means the excitation will be supplied from the grid, not from the capacitor. It is already shown here, no capacitor is connected. You can connect capacitor, no problem, because then the capacitors will be excited from the grid and supply some reactive power to the induction generator. Then the reactive power taken from the grid can be reduced. You can connect it as well, but it is not a mandatory situation. There it was a mandatory situation. You have to connect capacitors, otherwise it will not generate, right? Now here this excitation is actually taken from the grid. Now, as excitation is taken from the grid, it is actually at grid frequency. Now in earlier case, as excitation was taken from the capacitor and the generated voltage, the generated voltage was at variable frequency. So naturally, variable frequency excitation was there and variable frequency generation was there. But here, naturally, fixed frequency excitation is there and the generation also will be at fixed frequency, right? So then come back to this characteristics. So this is the generating region. So for this grid connected system, now you see that the generation is only possible at super synchronous speed, right? As you know that some field is already excited there, and super synchronous with respect to the grid excitation. Say I am giving you an example. Say you have a 4-pole induction generator and connected to a 50 hertz grid, 4-pole 3-phase. So naturally, its synchronous speed is 1500 RPM. So generation can only be possible above 1500 RPM, right? Now this generator has some rated sleep. So this is actually rated sleep. So rated sleep basically say usually tends around 4%, 4.5%, 3.5% like that. So take an average of 4%. So 4% rated sleep is actually 60 RPM. So at 1560 RPM, this generator is supposed to generate rated power. And if there is an increase in speed, so power will increase, but at the same time, sleep is also increasing, and that extra power will actually result in excessive current from the stator terminals, and the motor will be heated, generator will be heated. So you cannot have additional power generated from this rated, say for 1 kilowatt generator. So if you try to generate 1.5 kilowatt, so what will happen? Naturally, voltage will, current will increase, and the machine will burn. So therefore, it will generate at a speed around 1560 RPM, appreciable power. And if speed falls to lower values, above 1500 though, so the generation decreases, right? Because P is omega T, so torque is decreasing sharply. Now, if it falls below 1500, then it will come back to motoring. So normally, it is a fixed frequency system. It's a fixed frequency system. So here, there it was variable frequency. Here it is a fixed frequency and fixed speed system. Fixed speed. Say it has to rotate around 1560, 1540 to 60, around this 20 RPM variation is possible. But with wind speed being varying widely, it is not a really feasible situation that we expect it to run at fixed speed. Usually gear systems are used with wind speeds that can change the turbine speed into a fixed one, but this is not a very smooth control. So smooth gear is not possible. The gear change maybe 1, 2, 3, 4 steps, and within that, whether it is there, it can do. Else, there is some other system. We have to shut down the system. So this is what the generation with the grid connection, right? And loads also can be connected. So now came the, all these things require very less power electronics, isn't it? The induction generator schemes. This was actually the oldest scheme because here this is a generation, and this also there is a generation. We don't require any power electronic converters, anything. Even synchronous generators also, if you don't want to convert this frequency, variable frequency to fixed frequency, you don't require much, only a rectifier. Rectifier was known even 100 years back. So actually, it was possible. But then came the beauty of the power electronics, where people tried to convert this squirrel cage induction generators into a variable speed generating unit, and then connecting to the grid. How? The situation is similar. The situation is similar to the synchronous generators we have seen with back-to-back converters. Now here, this squirrel cage generator is connected with a converter, and this converter is again a bidirectional converter, active front end. It can supply reactive power like that synchronous generator, but I was talking about. It was not shown. It was there. It was only rectifier. I told that it can be possible. Now here is the possibility. Now this one we have already shown here. So this one will supply reactive power corresponding to the speed, right? Corresponding to the speed of the turbine. So that this is always running at super synchronous speed. The frequency is generated in that way, right? And within the say 4% stage of the rated torque situation, right? So then actually the reactive power is supplied at variable frequency and active power is brought at that frequency, and then it is dumped here at the DC bus after rectification, right? So active power is dumped in the DC bus after rectification, and then this DC power is again converted to AC power with the help of the grid side converter, right? And then at fixed frequency and fixed voltage as per the grid utility voltages. And if voltage does not match, frequency can be easily matched, voltage doesn't match, we can have a transformer also for interconnection purpose. So this made the generation possible, from variable speed system through squirrel cage generators. Now again, you see, this system will have the drawback, similar drawback, that it will require two large converters of equal rating of that of the induction generator, isn't it? Induction generator 1 megawatt, this active front end converter has to be 1 megawatt, and this grid side converter has to be also 1 megawatt. So again, the question of say high cost, then high space requirement, and then reliability reduction, everything is there. So here cost of converters are high. This is the major disadvantage. Otherwise, it is having some good advantages. Best use of wind power. Why? Because we are able to generate from variable speed situations, right? We don't have to discard certain speeds or something for generation. But of course, this discard speeds should be above the cutting speed of the wind turbine. If the wind turbine has to rotate fast, so rotational speed has to be maintained. So this is what this squirrel cage generator schemes. Now this is actually the concept in detail diagram that generator side converter and grid side converter, and then we have a transformer equivalent say reactance given, leakage reactance, and this is what is there. Now these two are okay. Now came the synchronous slip ring type of generator. Slip ring, right? Slip ring type of generator. Now slip ring generators, have some advantages. What is the advantage? The main advantage is that the rotor is accessible. Now when rotor is accessible, so you can do something like say insert some resistance in the rotor, and then if rotor resistance is inserted, what will happen? Now you can shift the characteristics, right? Now this, this one. So you shall look at this figure where we have shown the characteristics at different rotor resistances, right? At different rotor resistances, increasing rotor resistances in the generator side, not in the motor side. You have generally seen it at the motor side in your classes or in your textbook. Now generator side, if you see, now when external resistance is 0, the normal characteristics. When external resistance is little higher, is this second one, then further higher. Now how does it help you? Now if it is clearly seen here that as you have to run it near rated torque, as I have said, that near rated torque to make best use of wind power, right? So this rated torque appearing at higher slips. Torque is rated, but it is appearing at higher slips. Supposing it is appearing at 10% higher slip, that means there it was 4%. So we were getting here at 1560 RPM. Usually it is around 15% we can reach. So 1560 RPM here we reached. If you remember my just a few minutes back, I showed you. Now this 1560 RPM can be extended to say 15% of 1500 is how much? 150 plus 75. Say another 225. So 1725. So 1560, instead of 1560 RPM, we are getting same torque at 1725 RPM, right? That means speed variation of wind is possible here, right? And with higher wind speeds, we can insert more and more rotor resistances so that we can get rated torque. But there are certain problems. We cannot extend it to very high values simply because those high values will make the rotor losses high. I mean, the advantage which you are getting there by having some extended speed range, that advantage is actually eaten away by rotor losses. So rotor loss will be high, so that you cannot generate much power. So right. So and heating also will be very high. So usually it is restricted around 10 to 12% or at the most 15%, right? So this is the idea, and this was actually achieved through this method. So resistance was changes to this chopping IGBTs. Now when this IGBT was on, the resistance was sorted, and when the IGBT is off, the resistance is in the rotor circuit. So varying the duty ratio of this IGBT, we can have effective resistance change. So R effective equal to R into 1 minus D. So this way you can derive. Okay. Now the soft starter is actually due to the higher voltage. When higher voltage is generated, we can truncate it through this back-to-back converters, back-to-back thyristors, and then send it to grid. So these are all there, right? So, so these things actually these are explained here. Rotor, same thing what I have told, has explained. Now the same thing has been converted in power electronic circuit in this way. This rotor side converter and grid side converter. This rotor side converter is effectively virtually changing the rotor resistances. Virtually changing means it does not produce any additional rotor loss, right? Because it is a virtual resistance, right? And then this is the grid side converter, which is converting this DC voltage to grid. Now this is known as DFIG, doubly fed, means stator is also feeding, rotor is also fed, or stator sometimes feeding power, rotor is extracting power. So general term is doubly fed induction generator, and it was actually termed from doubly fed induction motor, DFIM, and then it is DFIG. Now why? How does it help you? Just to see here. Now this rotor side converter, is connected to the rotor. Now rotor power is actually the slip power. If you remember the Servius system, static Servius system, static Kramer system for speed control of induction machine, the concept is same here. There actually rotor power was controlled to vary the speed, and rotor power was the slip power, small power. So here also this rotor power is controlled for generation purpose. Now how does it help you? Now in these earlier cases where we had to connect the converters in the stator, the converters were handling the full stator power, right? It is 1 megawatt, 1 megawatt, and to 2, of course, 2 converters. Now here rotor power is slip times the stator power. Now if slip is 4%, so for 1 megawatt power, you have only 40 kilowatt power here. If the slip is 10%, for 1 megawatt power, you have 100 kilowatt power here. And if the slip is 30%, we can go up to 30%. For 1 megawatt power, we can have 300 kilowatt power. That means with controlling smaller amount of power, we are able to control the entire stator power, right? So this is the beauty of this, and this scheme has really eliminated all other schemes normally for wind power generation in large scale. So whatever wind power generator you find, 99% or even more than that is this DFIG scheme due to this advantage. And it has got another major advantage. So the same things are written here. I'm skipping these few slides. So another thing we can show, but the times are running away. So actually another thing we can show by analyzing the equivalent circuit is that we can run the generator. I'm not I'm running through this because you will not be able to finish the last portion which I wanted to tell, means by another 20-30 minutes. So by adjusting the rotor power, we can even run this as generator below synchronous speed. So in earlier situation we have already told you that the induction motors when grid connected will operate as generator only above synchronous speed, isn't it? But here the stator is grid connected, here the stator is grid connected. But even then we can run this machine as generator below synchronous speed. And usually the claimed you can say slip below synchronous speed at which it can generate is around 35%. 30% is very common, right? And same the claimed speed of the generator, the machine running as generator above synchronous speed at 30% slip. That means the slip can vary to below 30% to above 30% from synchronous speed. Now again you take that example, 1500 RPM 4-pole machine. Now 30% slip, 30% of this speed is actually 450 RPM. So 450 RPM below synchronous speed is around 1050 RPM. Say roughly you can say 1000 RPM. Now 450 RPM again above synchronous speed is how much? Is 1950 RPM. Let us say roughly 2000 RPM. So we can have a variation of speed from 1000 RPM to 2000 RPM while generating electrical power, isn't it? So naturally it is shown in this power flow diagram. So this is the air gap power, which is actually the stator power. Let us say you neglect stator losses, so this is stator power being fed. Now when rotor power is inserted, right, rotor power is into the system, so it can generate below synchronous speed where we are feeding the stator power. This is the mechanical input power, is the rotor copper loss. So net power available is actually PAG minus P2, neglecting stator losses, because P2 we are feeding and PAG we are getting. And naturally PAG is more than P2 because mechanical power is there. So if you take this as node, so PM plus P2 is PAG. PM plus P2 is PAG, right? So this way you can think. And above synchronous speed, which is known as super synchronous, so here rotor is also delivering power and stator is also delivering power, air gap power. And mechanical power is actually PAG plus P2. PM is PAG plus P2. Naturally more mechanical power, it is driving it above synchronous speed. So both PAG and P2 is possible. So that is why we have said that this is a bidirectional converter, bidirectional. This can give active power during subsynchronous operation, active reactive power both during subsynchronous operation. It can bring active power and provide reactive power during supersynchronous operation. And this converter is also both bidirectional. Okay, so this way actually this is a revolutionary scheme, you can say. This has been actually, this paper was there from 1996, but commercially this scheme was available from 2002 or so. And after that you will find that wind generation scheme has been revolutionized, and a lot of research, thousands of papers are there on this, different issues like parameter variations, and then speed range extension, and then other things. Okay, so those who are pursuing research or will be pursuing research, they can seek into this field that can help them, right? So these are equivalent circuits, etc., etc. This is there, and then this is a phasor diagram. This things, okay, the same things are explained in different ways. So this is a part of a big lecture what I usually provide to some of the students also. And this is actually the MPPT control, which I skipped because that time the turbine was there. So the motto here, you are familiar with MPPT schemes for the solar systems, right? Usually, and the same can be available for the wind systems also. Now this is the plot of the power generated versus the rotational speed of the turbines, right? At different speeds, different wind speeds, ranging from 0.5 per unit to, say, this 1 per unit. You can take any, say, is the turbine rating usually. If the turbine is rated at, say, 20 meter per second as 1 per unit, so you can assume it is a 20 meter per second wind speed here as 1 per unit, and accordingly it will be scaled. So you can track these maximum power points by varying the rotational speeds with the help of your control. So I'm not going deep into that control. So this is what is there. So there are few modes. This is a parking mode. Parking mode means here it will not run. This is cut-in speed from which it starts generating. Usually in meter per second for wind speed, normally it comes out to be around 4 to 4.5 meter per second for horizontal axis large turbines, and for say vertical axis turbines a little lower, but the generating power is very less. Okay, so this is what. And then after that we have a generator control up to 1 per unit speed, and then we have a pitch controller where we can vary the pitch angle of the blades so that my power is not exceeded above one per unit. And then after that there will be a shutdown. Okay, there will be a shutdown. So you have to shut down it depending on the turbine rating. So MPPT schemes are mentioned there, different types based on wind speed. We can do it, and based on wind speed and lambda, is actually the tip speed ratio, and RT is the radius of the turbine. So this way actually we get omega, R omega like that. And then we can have a torque control also based on the torque sensing and omega M sensing, etc. So there are various ways MPPT schemes are going on. There are researches people are doing, and we can do it. And some schemes I will show in a brief, which is actually hybrid generating. Sometimes solar and wind, they are hybridized. We have also done certain small experiments or some experiments with some projects in our labs. So this is the way actually the DFIG scheme was modified, and this is also like this. And then there are some micro generation schemes from wind, right? Micro generation schemes from wind. We can have this kind of schemes of three-phase systems, and then this battery can be replaced by this battery can be replaced by some solar module also. So we can have hybrid generation, and then single phase motors also can be used for generation. And this is a battery, typical battery shown, but you can replace it with solar cell also. And then there can be three phase motors converted into two phase, and then used for generations. These are all some of our research work we are showing, and these are the control schemes. So normally now we will just next 10-15 minutes we will show that how you can introduce intelligent systems, how you can use intelligent systems into this type of generation. First of all, you should know how to generate, and then you should find that where we will make it intelligent, right? So now at the beginning of my lecture I stated that these generators are known as distributed energy resources, DERs, or distributed sources, DS sometimes. Now, these are usually connected with microgrids for local usage, and those microgrids will be connected to the major grid through power control center, PCC. That is what is shown here. It's a microgrid unit where several storage as well as your loads and generating units are connected. Of course, in between there will be converters. So converters we have not shown. This is a symbolic diagram. and then the whole microgrid can be connected to PCC. Now there can be a controller to control in a way that which has to operate or which is having higher capacity or higher power, and then power sharing between the sources, right? And not only that, say this PCC, supposing we are supplying to the load and the generated power, adding all, say, solar, wind, small hydro, biomass, they are not sufficient enough to supply to the load, right? Even storage is finished, right? And at that time, we can have that grid power available, right? Grid power taken, right? The arrow is bidirectional. And there can be situations where these powers can be excess. Load is light, then grid can be supplied by the microgrid. But in some situations can happen that we have deficit of power, but grid is also having some faulty situation. Grid has failures, or power is off, grid power. Then what will happen? Now then, this controller will be having certain intelligence to cater to critical loads, and at the same time, it will decide its own sharing between the sources. That means, supposing you have a 10 kilowatt solar and 10 kilowatt wind, and situation is such that solar power is almost only 1 kilowatt and wind is 2 kilowatt or 5 kilowatt, whatever. So the sharing will be according to the available power. So those intelligences it has to see, right? So this is the basics I'm telling. So from this, actually, the situation started that how we can provide efficient control and intelligent control, so that overall generation cost is actually minimized, as well as the sources are used to the best extent, and at the same time we are able to cater to the loads, right? So this is where the requirement for intelligent systems came. Now the classification of microgrid can be in this way: single phase, three phase, decentralized, centralized, AC, DC, isolated, grid connected. Now again, when the grid has failed, so there can be another intelligence for sensing that the grid has failed. Now it will come back to isolated mode of control, islanded mode. It is known as islanded mode, grid connected mode and islanded mode. So identification of this operating status is also another intelligence. Okay, so therefore there can be various researches. There are various researches that have been going on, and those who are really interested, they can look into papers in say IEEE journals like, say, Smart Grid, IEEE Sustainable Energy, IEEE Power Delivery, this type of transactions. Okay, so that you can find thousands of papers dealing with different things, right? So these are things. Now another thing, after I was talking about energy management, right? So energy, how will you manage the available energy? Now there are certain forecasting also. Sometimes that can be used. Now here the loads, the consumption. This, whatever I have said are all said in this type of say blocks. What we are showing. So the control modes are like this. So you have renewable sources, you have forecast, and then the consumption, the load also has to be estimated, and then this is actually energy storage system state. How much storage you have, say the battery state of charge. So what is the amount of state of charge you are having? Whether we can discharge or recharge the battery, or just shut down the battery, which way. Then the market price also, there can be another issue. Then import-export power at the PCC level. So it will decide. Then dispatchable power control, local level, customer level, or the demand side control. So these things are really, I mean, you can say integrated with your intelligence systems. Now, artificial intelligence methods that are really used are these: neural networks, evolutionary algorithms, fuzzy logics, and multi-agent iterative methods are there, and then predictive control, integer linear programming, stochastic and robust programming. So all these things, they are getting slowly applied in these fields as a research work. Okay. So now again, centralized control, there are different controls, centralized and then decentralized. Now, energy management system can have a central controller to control all that it's starting with that. So management system control, and then the centralized control, which gives command to all the controllers. I mean, all the sources as well as to the load as well as to everything. Okay. And then there can be a scheme of decentralized control where we have grid, but depending on the situation of the grid, taking feedback from the grid, whether it is connected or grid connected, or grid means microgrid I am talking about, DC grid, AC grid, whichever way. So depending on the situation, it will decide that what will be my generation, what will be my frequency, whether it will follow the grid, whether it will dictate the grid like that. So these are the centralized and decentralized. And some optimization techniques are also there to actually control it. I am showing all the outlines because detailing, if I go, only one detail will take 2 hours, 2.5 hours. So it is not, I mean, I'm giving you some foundations where you can start, do some work. So recognition of problem, defining, model construction, problem solving, and these are actually basic, I mean, you can say flow chart for the optimized algorithms. I'll show you one example if I get time, maybe another 10-15 minutes I will be able to speak. My voice is not really proper due to some. Yeah. Now, classification of control methods, as I have said, there are different control methods, like say conventional and novel techniques. Novel means actually these were known from earlier, but we are using those tools. We are using those tools to make the control finer or quicker or sometimes better, like that, right? So conventionals are group control, master and slave control, virtual impedance-based group control. This is also another, sub part of group control, MPPT, and master and slave we have already written. I mean, by mistake it is given 2 times. And then the other techniques are supervisory, intelligent, and adaptive. Okay, so these are highly control-oriented techniques. Those requires very high computational intelligence and high-end processors, and usually not feasible sometimes also. Theoretically, we can say that this is happening. This can happen like this, like that. Now, a general structure for the grid source combination, if you see, grid means say microgrid, and then that DG sources, right? Say we can have this type. Say we have a DG inverter, distributed generator inverter, and then this is a grid. Now grid will have its own impedance, and inverter will have its own reactor for interconnection or impedance for interconnection, and they can share a load. So this way the thing will come, right? And we can have different sources also, not single sources, even 2 sources, 3 sources. If you look at this diagram, there can be many sources. Even the first diagram, this one, many sources. Now this has resulted in this diagram, many sources like that, and we have shown it for a single source. Now just I am showing for the droop one. Now the droop means actually it's real power and reactive power. Means active and reactive power will be controlled through certain variables. Like say, active power will be controlled with the help of the operating frequency, right? So if you remember your generator characteristics, alternator governor characteristics, frequency, power frequency. plot. It is simply like this. So the same thing we are going to introduce here, power with frequency. And this, I think you can say that this is FR is the rated frequency, F is the frequency reference to be given. And M, we have designed this way. You can design in a different way, right? This 0.5 P rated minus P star. P star means P reference. Now, if P reference is higher than 0.5 PR, right, the frequency will be reduced from the rated frequency. FR is here. FR will appear at 0.5 P rated. So this is what we have seen, right? Now, designing this M is really a tough task because this M is the factor through which you will multiply this 0.5 PR minus P star so as to arrive at your rated frequency, right? This M can be defined through some fuzzy logic. It can be defined through some, say, evolutionary algorithm. It can be obtained through some, say, PI control output. So various ways. So these are the things that on which researches are going on. Similarly, reactive power, this factor in, this is highly dependable. So this way, we can really look into our control. Now, the comparison of control methods, if you see, the novel control and this, as I have said, these are having computational complexity, highly computational complexity. You cannot do it in a ordinary processor or without having some PC of high-end PC, you can say, in many of the systems. But other things are really applicable in physical systems. It is really, you can say, it is coming, right? So, these are the different techniques, benefits, and limitations, right? And then you see there are another control-wise, hierarchy-wise. You can have a primary controller, we can have a secondary control, we can have a tertiary control. So primary control is at the base level. It is voltage, current, state of charge, MPPT, load. And secondary is actually a little bit higher. We have a droop, we have a power flow control and sharing strategy. And tertiary, again, energy management system, optimal power flow. Those, I mean, you are rising above this pyramid. You are reaching more and more computational things and more complex things, rather, and at the same time more precise things, right? So these are the things. Now, primary control with some intelligent control, you have power calculations, bus, filter, and then finally it will control the DG. PWM will control the DG. And then we have a primary controller agent which decides the voltage and frequency, right? Voltage and frequency. And then it gives a reference, and then at the same time, it will go to voltage, current, loop, and PWM. It is easier. And when you have the secondary control, we have some agents coming from the secondary controller, and that will further refine your primary controller agent output of, say, voltage and frequency, and then give a refined voltage and frequency, and you have a preciser control. And taking into account those things, like, say, from the droop, from the sharing strategy, from the power control, whichever way you require. And again, the tertiary control gives something, I mean, that economic dispatch, energy dispatch, and all those things, this machine learning algorithms, and then it gives tertiary control agent, I mean, some input to this secondary controller, which actually, again, uses them to refine its delta U and delta F. And then again, this delta U, delta F refining this U and F. The primary. So, okay, hierarchical control comes and we get. And there are, you know, certain power quality problems that can arise with these controllers. So, like, say, inverters introducing harmonics, and then voltage and frequency drooping, and limitations over inverter rating, switching oscillations, and all those things. And to avoid that, we can have certain, you can say, techniques also. So the frequencies are decided by this IEEE 1547A specifications. And then these are things, they are theoretical things. Normally, I will show you one thing and end it. This is actually, say, our research work long back. So actually, instead of fuel cell, we had used some batteries and all, but we showed it as it. But the thing is that fuel cell characteristics we introduced here. But the thing is actually that how the harmonics are reduced. That's the most important thing. Now here, actually, two sources are shown, two DGs, two DGs. One DG is this one, another DG is this one. Now, when we switch or when we connect, so some harmonics are introduced here, right? Now, if we have some intelligent controller which actually can assess that injected harmonics here and then controls this one in such a manner that this also injects harmonics, the same harmonics in opposite phase. So overall harmonics will be reduced. So this was actually utilized by us by designing some selected harmonic elimination PWM, SHE PWM, by eliminating some few lower order harmonic like 5th, 7th, and 13th. And we have used, in order to generate those triggering pulses, we have used PSO, particle swarm optimization there. So I was showing that that heuristic method based algorithms also can be used. So this is PSO we have used. Now, when we have shown the dotted one is actually the sine PWM, which is actually for one inverter, and another one is PSO PWM, its own, and it is showing the voltage THD actually. But when these two are combined, we get overall THD of the voltage, grid voltage, which is actually much lower compared to any of this, right? So this is what things are going on, and they are attempted in a different manners also by other researchers. And this is overall harmonic criteria that simulated and experimental we had achieved. So that's all. So thank you very much for your patience, and I appreciate if you have gathered something, or if you are getting interested after the lecture with some research work in the same field. And if you feel that some portions will not clear to you, my phone numbers and this email IDs are there with the organizing committee. You can come, and now you can, a few small questions, definitely you can ask by next 5 or 10 minutes. I will try to answer. Okay, so thank you very much.
So all the participants are requested to ask any questions if you have any doubts. So sir is there. All of you are requested to ask any question regarding this session.
So no questions. I mean, everybody have either understood everything, or they are not really interested in this kind of say research work or this kind of work. Is it? Or they have gone for dinner. It is too late.
Okay.
Okay.
Sir, we will take a photograph. So yes, anyone want to ask the question?
Then I will.
Yes.
Hello.
Good evening, sir.
Good evening.
Yes, Sharma.
So you have not gone to lunch. Hey, you have gone to dinner.
I'm listening to your PPT.
Tell me, you have some questions.
Sir, my general question in case of selected harmonic elimination,
Ah.
which this question also be I have asked yesterday. What is the main advantage or optimal solution with respect to third harmonic injection or selected harmonic elimination in case of any harmonic mitigation process in THD?
See, selected harmonic elimination means actually these converters when they are connected, or we can have others also. Just the lack of time, multi-level and all I have not discussed. Thing is that when the inverter gives some waveform, say a two-level three-phase inverter, it will have certain harmonics in the system. Now, if you design the triggering angles in such a way that you remove those, say, lower order harmonics, say, let us say, we have given example here, say, third, fifth, seventh, 11th, and 13th, right? You can set it. Now, these harmonics are removed. Now, when these harmonics are removed, the other harmonics will increase, right? So, so what will happen that if one selected harmonic, if you give third, fifth, seventh, and 13th as some optimum value, not totally removed. So in that case, the other harmonics also can be controlled. So this is one way. Now another thing is that if those things are present, then you can design a second system which removes third, fifth, 11th, 13th to a lower extent, but produces the other harmonics which was there by the first one in opposite phase, right? And same magnitude. So then overall thing, your total harmonics will be reduced. So selected harmonic means you design the equations. You design the equations in a manner that these harmonics are either removed or controlled. Right? Elimination means zero, but normally they are not eliminated in many ways. They are actually mitigated or they are reduced to a very low extent.
Okay. But not properly totally diminished.
You can reduce totally, but in that case, your other higher order harmonics may increase also. That you have to see by seeing the spectrum or seeing the output calculation.
Total harmonic distortions will be decreased or increased?
Weighted harmonic will be decreased. Total harmonic distortion have some decrease definitely, but not to that extent, unless and until you do that. So it's a very trivial way to choose it. Means how much you require to reduce, and then other will be controlled like that. This is again a question of mixed things. This particle swarm and then some other intelligence. So those things also a matter of research, you can say. Yeah.
Okay. Okay. Thank you, sir.
So, okay, anybody having doubts? I think nobody have any doubts. So, thank you, sir. Thank you very much, sir. Now I conclude. So, on the behalf of organizing committee, I sincerely thank Professor Dr. Devashish Chatterjee, sir, for graciously stepping in at a short notice period and delivering such an insightful session. And your willingness to support us despite the sudden change reflects your commitment to share your knowledge, sir. Your valuable expertise has not only deepened our understanding, but has also truly inspired each one present over here. Once again, thank you, sir, and all the participants for being with us today and make the session truly remarkable. So, thank you, sir.
Sir, please,
Yes, sir.
please stay with us. All the participants are requested to switch on the video so that we can take the photo with sir. All of you are requested to please switch on the video. Okay, thank you so much.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir, so much, sir.
Thank you. So
Thank
I
you,
am
sir.
leaving now. Huh?
Sir.
So I am leaving now.
Yes, sir.
Yes, sir. Yes, sir. Dear participant, I request all of you to kindly fill up the feedback form for this session. And the link already being shared in the chat box. I think already shared.
So I'm leaving. Huh? Okay.
Sir. Thank
Yes.
you, sir. Sir. Your feedback is very important for us and also required for AICT record. Okay, kindly submit your feedback. Okay, dear all, with this, we come to close of day 3 of our FDP on computational intelligence and application in power engineering. A heartfelt thanks to our respected speaker, Professor Dr. Kalyan Chatterjee and Professor Dr. Devasis Chatterjee, for enlightening us with their rich expertise and for making today's session truly insightful. We also extend our gratitude to our participant for your active engagement and valuable contribution. Thank you. On this note, we officially conclude day 3. We look forward to welcoming you again tomorrow sharp at 6 p.m. for day 4. Thank you and have a nice evening. Thank you all.